A is multiple of B if there exists an element X in R such that A is equals to Bx. So A is equals to B into X. So we can say that B is divides A, or B is divisor of A is divisible by B, or A is multiple of B. So A is equals to Bx. In this case, so we write B divides A. We use the symbol B does not divides A to say that B does not divides A. So this is nothing but B divides A. So this is the notation. So B divides A, and so this is nothing but B does not divides A. So this is divisibility condition. So once again, divisibility condition. If A and B are non-zero elements in a integral domain Kepler, so we say that B divides A, or B is a divisor of A, or A is divisible by B, or A is multiple of B if there exists an element X in Kepler such that A is equals to Bx. In this case, so we write B divides A. So we use the symbol B does not divide A. So this is note point. If A comma B and C be non-zero elements in R, then so A divides B and A divides C. That implies A divides B and B divides C. So that implies A divides C. So this is the first condition in divisibility. A divides B and B divides C. So that implies A divides C. So next second condition, A divides B and A divides C. So A divides A plus or minus B plus or minus C. So this is second condition. A divides B plus or minus C. And third one, A divides B. So that implies A divides B into X for all X belongs to R. So these are the divisibility conditions. Next definition. An element A in a ring Kepler is called unit in R. So unit definition, unit in R, if there exists an element B belongs to R such that A into B is equals to 1. So A into B is equals to 1. So that is a unit ring in element which has multiplicative inverse in a ring. So clearly an element U belongs to R is a unit if and only U is a divisor of 1. So unit element is nothing but A into B is equals to 1. So definition, an element A in a ring Kepler is called unit in R if there exists an element B such that A into B is equals to 1. So A into B is equals to 1. So A comma B belongs to R. So A comma B are units. So A into B is equals to 1. So this is unity definition. So next, two non-zero elements A and B in R is said to be associative if A is equals to U into B for some unit U in R. So we write A is associative to B to say that A and B are associative to each other. Okay. So this is associative property. A is equals to U into B. So but U is unity element in R. So U is unity element in R. So then we can say that A comma B are associative. So it is denoted by A is associative to B. So this is notation. Next definition. So let A1 comma A2 comma to AN be non-zero elements of an integral domain Kepler. An element D belongs to R is said to be a greatest common divisor. So this is nothing but GCD. So D is said to be a greatest common divisor, GCD of A1 comma A2 comma up to AN if D divides AI for all 1 less than or is equals to I less than or is equals to N. So D is a common divisor of all AI. So if for C belongs to R, so C divides AI for all 1 less than or is equals to I less than or is equals to N. So then C divides D. So we denote any greatest common divisor A1 comma A2 comma up to AN by the symbol GCD of. So this is a symbol of GCD of A1 comma A2 comma up to AN. So this is a GCD definition. This is LCM, least common multiplier. So let A1 comma A2 comma up to AN be non-zero elements of integral domain capital R. An element D belongs to R is said to be a least common multiple LCM of A1 comma A2 comma up to AN if AI divides D for all 1 less than or is equals to I less than or is equals to N. So D is a common multiplier of AIs. So second one, if for C belongs to R, so AI divides C for all 1 less than or is equals to I less than or is equals to N. So then D divides C. So this is the LCM, least common multiply. So next definition, prime ideal, prime and irreducible elements. A non-zero element P of integral domain, so with unity, is called prime element if P is not a unit, and if P divides A into B, then P divides A, or P divides P for any A comma B belongs to R. So this is prime element definition. So a non-zero element P of an integral domain capital R with unity is called prime element if P is not a unity element, is nothing but, so P is not a unity, and if P divides AB, so that implies P divides AR, P divides P for all A comma B belongs to so R. So next definition, irreducible element, a non-zero element of integral domain R with unity with identity is called irreducible element if A is not a unity and every divisor of A is improper. So improper is nothing but A is equals to B. So B comma CR belongs to R. That implies that either A or C is unity. So A is equals to BC. A is equals to BC. In these two elements, at least one element is so in these two elements, so one element is unity. So A is equals to BC. So in these two elements, P or C is at least one element is unity. So then we can say that so A is irreducible to B. Next, so this is very important topic. Principal ideal domain. Principal ideal domains. So definition: an integral domain in which every ideal is principal ideal. Principal is called principal ideal domain. So in shortcut, PID. So principal ideal domain. An irreducible element in a principal ideal domain is always prime. So this is very important theorem. Every principal ideal domain is unique factorization domain. So principal ideal domain and unique factorization domain. So unique factorization domain definition. So this is UFD definition. An integral domain R with identity is said to be a UFD or unique factorization domain. It satisfies the following conditions. So any non-zero element in R is either a unit or it can be written as product of finite number of irreducible elements of R. So second condition, the decomposition in equation 1 is unique up to the order of associate of the irreducible elements, that is A is equals to P1 comma P2 comma up to Pn equals to Q1 comma Q2 comma up to Qm are two factorizations of A into its irreducible elements, then n is equals to m, and each Pi is associate of some Qj and vice versa. So this is UFD definition. So this is very important theorem. Every principal ideal domain is unique factorization domain. 10.6.4 theorem. Every principal ideal domain is unique factorization domain. So theorem, every principal ideal domain is unique factorization domain, or every principal ideal domain is UFD, but converse is not. So this is theorem statement. So before going to theorem, so first we have to see the principal ideal domain definition and UFD definition. So principal ideal domain definition is nothing but UFD definition. Unique factorization domain. A commutative integral domain R with unity is called UFD. Every non-unit is a product of finite number of irreducible elements. Every irreducible element is in R is a prime number. So example, z comma plus comma dot is UFD. The ring of polynomials of f of x is UFD, where f is field. So this is very important theorem. Every principal ideal domain is unique factorization domain. Proof. Suppose R is the principal ideal domain. So our assumption R is capital R is a principal ideal domain. Then R is commutative integral domain with unity. So we know that every principal ideal domain is commutative integral domain with unity. So R is commutative integral domain with unity. So first we show that R is principal ideal. So we have to show that R is principal ideal. Then R cannot have infinite properly ascending chain of ideals. So first we have to show that R is principal ideal domain. Then R cannot have infinite properly ascending chain of ideals. So if possible, suppose that our assumption is nothing but, so R has infinite properly ascending chain of ideals. So suppose that A1 into R subset R is equals to A2 into R subset R is equals to up to infinite numbers is an infinitely properly ascending chain of ideals in R. So this can be written as capital A is equals to, so capital A is equals to union I is equals to 1 to infinite. So union I is equals to 1 to infinite. Union I is equals to 1 to infinite. AI into R. So substitute A is equals to 1, I is equals to 1, A1 into R, subset R is equals to A2 into R, subset R is equals to up to infinite. So this is nothing but infinite properly ascending chain of ideals. So capital A is infinite properly ascending chain of ideals. Now we have to prove that A is an ideal. So capital A is nothing but union AI into R. So U is equals to A is equals to union AI into R. I is equals to 1 to infinite. So now we have to prove that A is an ideal. So ideal, we have to show that ideal A is capital A is ideal. So ideal is nothing but, so ideal, how to verify A is ideal? So A minus B belongs to capital A. First condition of ideal. The first condition of ideal, A minus B. So first condition, A minus B belongs to capital A. So in ideal definition, so first condition, A minus B belongs to A, and second condition, left ideal comma right ideal belongs to capital A. So A into R comma R into A belongs to A. Okay, so A minus B belongs to A and A into R comma R into A. Left ideal line, right ideal also belongs to A. So then we can say that A is an ideal. So now we have to prove that A is an ideal. So let A comma B, small element. A comma B belongs to A. Then A comma B belongs to capital A is nothing but, so union of I is equals to 1 to infinite AI into R. So the two elements are belongs to capital A. The two elements are belongs to capital A. So we can write A equals to union of I is equals to 1 to infinite AI into R, and B is equals to union of I is equals to 1 to infinite AI into R. So these two elements A and B. So next A belongs to union of I is equals to 1 to infinite AI into R, and the same element A belongs to union J is equals to 1 to infinite. So here we can split A can be splitting as I is equals to 1 to infinite, and also J is equals to 1 to infinite. Here two terms, I is equals to 1 to infinite and J is equals to 1 to infinite. A can be belongs to A is belongs to I is equals to 1 to infinite. The same element belongs to J is equals to 1 to infinite. Okay. So next, A comma B belongs to, these two elements belongs to I is equals to 1 to infinite, as well as these two elements are belongs to I is equals to 1 to infinite. Half an hour and only call you. Call you. So here A comma B belongs to I is equals to 1 to infinite AI into Ri. So these two A comma B belongs to I is equals to 1 to infinite and J is equals to 1 to infinite. So here A minus B. So A minus B belongs to I is equals to 1 to infinite AI into R. So A minus B, same A minus B also belongs to, so J is equals to 1 to infinite AJ into R. So A minus B belongs to I is equals to 1 to infinite. The same A minus B belongs to J is equals to 1 to infinite. So here I is equals to 1 to infinite, J is equals to 1 to infinite is nothing but capital A. So we can split the capital A into I is equals to 1 to infinite. So J is equals to 1 to infinite. The union of I and J is capital A. So these are two belongs to A minus B belongs to capital A, because these are belongs to A. I is equals to 1 to infinite and j is equals to 1 to infinite. So a minus b belongs to capital A. So therefore, first condition of ideal. So this is the first condition of ideal. So a minus b belongs to capital A. So similarly, we can prove. R into A and A into R. So left ideal and right ideal. So these are also belongs to capital A. For A belongs to capital A, comma R belongs to R. So therefore, A is an ideal in capital R. So ideal condition. So first condition of ideal, A minus B belongs to capital A and A into R, comma R into A belongs to capital A. So these are the two conditions of ideals. So here this is the first condition. A minus B belongs to capital A. So this is the first condition of ideal. So but A is nothing but so infinite properly ascending chain of ideals. So this is. So A is equals to union I is equals to 1 to infinite AI into RI. This is nothing but so infinite properly ascending chain of ideals. So this is A1 into R subset R is equals to A2 into R subset R is equals to up to infinite. So this is capital A. So here A minus B belongs to capital A and similarly R into A. So A into R. These are no need to prove that A into R and R into A also belongs to capital A. So for A belongs to A and R belongs to R. So therefore A is an ideal of R. So this is the first one. So next second one. Since R is principal ideal, so principal ideal domain, then A must be principal ideal domain. So here is given R is principal ideal domain. So then A must be principal ideal domain. So A is equals to generator of A. So A is equals to generator of A. So this can be written as A into R. So generator of A can be written as A into R. A is equals to generator of A, that is equals to A into R. So capital A is equals to A into R. So now A belongs to A into R because so A is an element of A into R. So A belongs to A into R. So but A into R is equals to A into R is equals to A capital A. So therefore A belongs to capital A. So A belongs to capital A. So A belongs to union I is equals to 1 to infinite AI into R. So replace A value. So small a belongs to capital A. So A belongs to union I is equals to 1 to infinite AI into R. So A belongs to AK. So this can be written as so this one. So this can be written as union I is equals to 1 to infinite AI into R can be written as so AK into R for some K. We are taking finite number. A belongs to AK into R for some K value. So therefore, A subset R is equals to AK into R because A is belongs to AK. Because A is belongs to AK. So here replace small a is equals to capital A is subset R is equals to AK into R. So but AK into R is subset R is equals to A. From these two conditions, so we can say that A is equals to AK into R. A is equals to AK into R. So here A is equals to AK into R. So next extension AK into R equals to AK plus 1 into R equals to AK plus 2 into R up to A. So hence R cannot have infinitely proper ascending chain of ideals. So R is principal ideal domain. Is clear? So this is finite. R cannot have infinite properly ascending chain of ideals. So but we are getting only finite number of chain of ideals. So these are finite number of chain of ideals. So therefore R is principal ideal domain. So this is the first part, first case. So first one, we have to show that every principal ideal domain is U have D. So we are taking R is principal ideal domain. So next we have to show that. So next, suppose A is not a unit in capital R. If A is irreducible, then there is nothing to prove. So second condition of so the second case. Suppose A is not a unit in R. If A is irreducible, then there is nothing to prove. If A is irreducible, so A can be written as A is equals to B into C. If A is not irreducible, A is equals to B into C, where B and C are not units in capital R. So we are taking A is not a unit in R. So but A is not a irreducible element. A is not a irreducible element is nothing but A can be written as B into C. So A is not a irreducible element is nothing but A can be written as A is equals to B into C, where B comma C are not a units in R. If possible, B and C are product of finite number of irreducible elements. So in this B and C, these two elements are product of finite number of irreducible elements. So then A is also a finite number of irreducible elements. So the product, these two product can be written as the product of finite number of irreducible elements. So then A also product of finite number of irreducible elements. So this statement, if B comma C are product of finite number of irreducible elements, then A also finite number of irreducible elements. So suppose here in this product, suppose B is not a product of finite number of irreducible elements. So B can be written as some E into F. So B can be written as some E into F. So B can be written as some E into F. So in this, so E and F can be product of finite number of irreducible elements. So B also product of finite number of irreducible elements. So but here in these two product, E is not a product of finite number of irreducible elements. So E can be written as E is equals to G into H. Here G into H is a product of finite number of irreducible elements. So then E also product of finite number of irreducible elements. So but similarly, same process. So G is not a product of finite number of irreducible elements. So similarly, so continue
excuse me, sir. That means it can be a prime number or what, sir?
not a
Cannot
prime
be
number. Cannot be irreducible is nothing but so irreducible definition in Japan among starting law. So A is equals to B into C, either A divides B, A divides B or A divides C అని చెప్పేసి డెఫినేషన్ ఉంది నాకు చెప్పాను. సో మీరు వేదనుకుంటాను చూడండి అమ్మ ఒకసారి డెఫినేషన్
Yeah, okay, sir. I'll look at it.
Okay. So suppose B is not a product of finite number of irreducible elements, then B is equals to X into Y. So suppose X is not a product of finite number of irreducible elements like this. B is E into F. E is not a product of finite number of irreducible elements. So suppose continue this process. So we are getting finite properly ascending chain of ideals. So continue this process. We are getting generator of A subset R is equals to generator of B. So like this. Subset R is equals to generator of C is subset R is equals to generator of D. So which is contradiction to our assumption. So both C and B and C must be product of finite number of irreducible elements. So hence A is a product of finite number of irreducible elements, because our assumption is nothing but B and C are the product of finite number of irreducible elements and B and C are not a unit elements in R. So units is nothing but the product of B into C is not is equals to 1. So these are the not a unit elements, and the product must be finite number of irreducible elements. Hence, A is a product of finite number of irreducible elements. This is last one. So we write an irreducible elements in commutative principal ideal domain. The converse of the above theorem is need not be true. That is, every UFT need not be a principal ideal domain. Every unique factorization domain is need not be principal ideal domain. So consider ring of polynomials f of x comma y, where x comma y are two independent variables. So here we are considering ring of polynomials f of x comma y. So where x comma y are two independent variables and f is a field. So here f of x comma y. So these two are independent variables, independent elements, and f is a field. So suppose f of x comma y is UFD. If possible, suppose that f of x comma y is principal ideal domain. So principal ideal domain is nothing but then there exists a generator. I is equals to I can be written as generator of x plus generator of y be the principal ideals in f. So let I is equals to generator of f of x comma y for all x comma y belongs to capital F. So x belongs to generator of x, but generator of x is subset R is equals to F. So similarly, y belongs to generator of y, but generator of y is subset R is equals to generator of f of x comma y. So here, so these two steps. X comma y belongs to generator of f of x comma y. So x is equals to c into f of x comma y. So this is by using the definition of ideal. X is equals to c into f of x comma y and y is equals to d into f of x comma y. So y is equals to d into f of x comma y and x is equals to, so after this step, x is equals to c into f of x comma y. So y is equals to d into f of x comma y. For all c comma d belongs to f. So f of x is equals to x by c. F of y is f of x comma y is equals to y by d. So x by c is equals to y by d. From these two equations, x by c is equals to y by d. So this can be written as x into d by c minus y is equals to 0. So but this is contradiction to our assumption. This is 0. So but this is contradiction to our assumption. So here x comma y are linearly independent. So linearly independent variables. So here linearly independent variable. So but we are getting x comma y are linearly dependent. Linearly dependent is nothing but so c1 into x plus c2 into x2 is equal 0. In these two c1 comma c2, at least one of the variable, one of the constant is not is equal 0. So here c1 is equals to d by c. So this is maybe 0, may not be 0, depending on c and d values. So, but here minus 1 is there. C2 is equals to minus 1. So this is contradiction to our assumption. X comma y are we are getting linearly dependent variables. So, but our assumption is nothing but x comma y are two independent variables in f. So f of x comma y are two independent variables in f. So therefore x comma y are we are getting x comma y are linearly dependent variables. So this is contradiction to our assumption. So hence x and y are dependent variables. So which is contradiction to x comma y are independent variables. So therefore our assumption is on every UFD is PID, principal ideal domain. Any doubts? So which is this is very important theorem. Every principal ideal domain is unique factorization domain.
Sir, can you please share the notes, sir, in group?
Okay.
Thank you, sir.
So this is a theorem in our textbook. Every principal ideal domain is unique factorization domain. So this is 10th chapter. So next, an integral domain R is said to be a Euclidean domain if for every a naught is equals to 0 in capital R. So there is a define a non-negative integer g of a such that the following conditions are satisfied. The first condition, g of a is less than or is equals to g of ab for any non-zero elements a and b of capital R. The second condition, for any a comma b belongs to R, so b not is equals to 0, then there exists t comma r belongs to R such that a is equals to t into b plus R. So where either R is equal to 0 or g of R less than or less than g of t. So this is nothing but division algorithm, based on division algorithm. So this is Euclidean domain definition. So this is the next theorem. Every Euclidean domain is principal ideal domain. Let A be an ideal and Euclidean domain R. If A is equal to 0, then 0 into x such that x belongs to R, that is equal to 0. So hence, so here if A is equal to 0, then it is principal ideal domain. So then there is nothing to prove. So it is directly principal ideal domain. Let A naught is equal to 0. Hence, there is an element A naught belongs to capital A such that G of A naught is minimal. So minimal since G takes on non-negative integer values. So now we have to prove that A is equals to A naught into X such that X belongs to R. So here we have to show that A is equals to A naught into X such that X belongs to R. If A naught is equals to 0 case, in case A is equals to 0, so it is already principal ideal domain. Let A belongs to A, since R is Euclidean and A comma A naught belongs to R, so we can find elements T comma R belongs to R such that, so this is totally based on definition. The definition of Euclidean domain, these two lines. So these total two lines are based on definition of Euclidean domain. Let A belongs to A, since R is Euclidean and A comma A naught belongs to R, so we can find elements T comma R belongs to R such that A is equals to A naught into T plus R, where R is equals to 0 or G of R is less than G of A naught. Now A comma A naught belongs to capital A and T belongs to R. So this is totally Euclidean domain definition. So but A is ideal of R, A naught comma T, A naught into T belongs to A. So this is based on ideal definition. So like A into R comma R into A belongs to capital A. So like this, A naught into T belongs to capital A. Therefore, R is equals to A minus A naught into T belongs to A. So first the condition of ideal, A minus B belongs to capital A. So here R is equals to A minus T naught into T belongs to capital A. So that is R belongs to A, and so G of R is does not subset R is equals to G of A naught. So because G of A naught is minimal. So if R is equals to 0, so that is, this is equation number 1. In equation number 1, R is equals to 0, A is equals to A naught into T for some T belongs to R. So therefore A is equals to A naught into X such that X belongs to R. So this is the theorem. Every Euclidean domain is principal ideal domain. So this is very short question. Every Euclidean domain is unique factorization domain. This is only statement. So next, ring of Gaussian integers. So next class, in next class, so this is the very, very important theorem, Einstein criterion for LAQ, long question. So next Saturday, we'll continue on next Saturday.
ఎక్కడున్నదా